Hello everybody. Come, let's go with Ampere's circuit law. Ampere's circuit law states that the line integral of the tangential component of magnetic field intensity, it represents H over a closed path in a magnetic field, is equal to the current enclosed by the closed path. In other words, the circulation of H equals I magnitude. So in the mathematical condition, I enclosed equal to surface integral of H into dl. By applying Stokes theorem to the left hand side of equation 1, that equation 1 represents what I told the previous. We obtain I enclosed a surface integral H dl equal to surface integral del cross H into ds. Also I enclosed equal to surface integral j into ds. Comparing both the equation I enclosed, we get del cross H equal to j. We should observe that del cross H equal to j is not equal to 0 because magnetization or magnetostatic field is not conservative. So del cross H equal to j is not equal to 0. If we have assumed F conductor carries a current I amperes, otherwise one conductor carries a current I ampere. This conductor having 4 paths, then except path 4, the other 3 paths can be found to enclose the conductor. But path 4 also a closed path but does not enclose the conductor. That means we make the mathematical equation surface integral path 1 is H into dl equal to surface integral path 2 same HDL equal of surface integral path 3 is HDL. So both 3 paths equal to total current of that conductor I. But surface integral of path 4 HDL is not equal to I. A useful law that relates the net magnetic field along a closed loop to the electric current passing through the loop first by Andrew Maria Ampere in 1826. This Ampere's circuit law states that the line integral of the magnetic field over a closed path or loop equal time the total current enclosed by that closed path. It has some applications that are magnetic field inside a long cylindrical conductor, magnetic field of a solenoid, magnetic field of a toroid coil. So if find the field intensity at a point P due to a straight conductor carrying current I, field at P due to a straight filamentary conductor. So dH equal to I dl into R by 4 pi R cube. This mathematical equation summarized by various substitutions of mathematical, finally we get H equal to integration of I rho dz a pi by 4 pi R cube. Then H equal to I by 4 pi rho cos alpha 2 minus cos alpha 1 into a pi vector. Unit is ampere by meter. So special case of this Ampere's law, The elements AB is extended to identify it is a infinitive at both the ends. Alpha 1 equal to pi and alpha 2 equal to 0. In that condition, magnetic field of H equal to I by 2 pi rho A pi vector ampere by meter. Then this Ampere's circuit law has another classification, that is magnetic field intensity along a point in the axis of circular ring carrying current. A ring of radius rho carrying a current. The aim is to find out the magnetic field intensity at the point P at the height h meter from the plane of the ring along the axis. A small element dl of angle d pi is considered. dh equal to idl into r by 4 pi r cube. So we can short out this indicated equation. dl equal to rho d pi a pi vector. So finally we get dh equal to I into rho h d pi a rho vector plus rho square d pi a z vector by 4 pi r cube. Due to symmetry, the a rho components will get cancelled because the radial components produced by pass of current elements 180 degree apart cancel. So we get h equal to I rho square by 2 rho square plus h square of 3 by 2 a z vector. Then boundary condition for magnetic field state. Consider the boundary between two isotropic homogeneous linear materials with permeability mu1 and mu2. At the boundary, the magnetic flux density B may be decomposed into a normal component Bf1 and a tangential component Bt, applying Gauss law for magnetic field on a small pillbox shaped. So mathematical condition is integral surface integral B ds equal to 0. So Bn1 equal to Bn2. This is boundary condition statement for magnetic flux density. So we can get a B2 vector minus B1 vector into An vector equal to 0. Normal component of B vector is continuous across the boundary between the two adjacent media. So this boundary condition always having the Maxwell equation of magnetic flux density. So it is very essential for this calculating method, because magnetic flux density represent B. So Bn1 equal to Bn2 is the tangential component of this boundary condition. So consider magnetic line away from the normal across boundary. The magnetic field intensity H1 is instant in media at an angle of theta 1 and H2 is reflected in media with an angle of theta 2. Similarly, beta 1 is instant in medium 1 and beta 2 is refracted magnetic flux density in medium 2, an angle of theta 1. Normally, magnetic potential having tangential component, from that boundary condition we picked the tangential formula also, tan theta 1 by tan theta 2 equal to mu or 1 by mu or 2. Let's see the next video. Thank you.